Okay, we've been walking through some coverage of the discrete time Fourier transform and looking at properties and the way to interpret this and how it relates back to sampling theory. The next item on the list from section 1.5.1 is looking at the discrete time Fourier transform from the viewpoint that it's a numerical approximation to the regular continuous time Fourier transform. Okay, so this is where he starts. He starts with a definition of a Fourier transform, although in this particular case, this signal here is the sample data signal. All right, so let's pick it up. Let's look at the definition of a Fourier transform more generally, okay, and then talk about how this can be numerically approximated and how that relates back to the sample data transform. Okay, all right, so let's first of all go back to Cal 1. All right, so in Cal 1 we did we did integration. I guess it's Cal 2, you probably did some numerical integration. And so when you're developing the theory of integration, one thing that you end up doing, I call it pushing rectangles. Okay, so you sample the signal and then you hold that for a time period cap t, all right, and then you have the area underneath the curve, and that's your first rectangle. Okay, so this sample value here would be, if this is f of t, then this first sample value would be f0. All right, then we take the next sample value, that would be right here, we would hold it, and then add the area in here. Repeating this process, sample values, hold, fill in the area, sample values, hold, fill in the area, everything spaced apart by cap t, and we end up with this as an approximation for an integral. Okay, so I think you get the idea. All right, each one of these is a sample value. Okay, so this particular dot, that would be f of t. This next one here would be f of 2t. And so we would have an approximation for the integral of f of tau d tau for t going from minus infinity to infinity by looking at the summation from n equal minus infinity to infinity of all the sample values. Okay, so that would be f of n t, all right, times cap t. All right, this would be an approximation for the integral, and as you let the limit as cap t goes to 0, let me move this over. All right, I need to make some space. Okay, what you did in calculus is you then took a look at the limit as cap t goes to 0, and you found that that was equal to the integral. Okay, so the cap t comes from the width, and you're adding up all the areas of the rectangles to give you the integral. Okay, so let's go back to the Fourier transform definition. All right, the Fourier transform definition is here, and so this part that I'm circling plays the role of f of t. Okay, so if I plug that in, I would get, just like I did here, sum of nt. All right, I would get the g sampled at every nt, which is what we have, multiplied by cap t. All right, So that's a numerical approximation for the Fourier transform. Well, if you go back and look at our sample data transform, remember what we had. If you started with an x of f, then what you did was you replicated the spectrum every fs. So this has the same shape as x of f, but the scale constant, if this had a height here of x0, the scale constant would be x0 over t. We'd covered that before. All right. So it does make sense, because what we're seeing here is you divide by t to get x hat of f. All right, and if you multiply x hat of f by cap t, the t's cancel and you end up with a numerical approximation for the Fourier transform. So that's what he's saying with this particular line in the limit. As the samples go to 0, you get an approximation for the Fourier transform. Okay, but what we also know is from the sampling theorem, if x of f is band limited, okay, x of t is band limited, then you don't need to sample faster than twice the highest frequency. You can still reconstruct the original signal. But from a numerical point of view, you can see why this would make sense as a way of sampling a signal and then interpreting the Fourier transform of that signal as a numerical approximation.